Hello, this is the part 6 boundary element design of the video series of special shear wall design using ETABS program. So in this video, we'll be going through the code requirements and the boundary element design of the shear wall we have been going through in our video series. In the first video, we have already discussed that there may be two types of boundary elements in a special shear wall. First type is the special boundary element, in which you have a boundary zone like this, and the hoops located or arranged in this boundary element are detailed in such a way that these conditions are met. So the hoop sets vertical spacing cannot be higher than b/3, where b is the boundary element width, 6 dB longitudinal, and these other formulas. And the boundary element calculation, the length of it needs to be calculated based on the following formula. So C is the neutral axis depth and LW is the wall length. This data can be found from the ETABS program. Okay, and the volume that you must fulfill, the amount of reinforcement that you have to provide as hoops reinforcement must fulfill this formula 0.09 S BC multiplied by FMC over FYT. However, in case of column, there was another formula which does not need to be satisfied in case of shear wall. So in case of column, you had another formula, which is this one, 0.3, and this SHC F prime over FYT multiplied by AG over ACH minus 1. So this formula actually governs when clear cover is high. When if you have, say, for example, 2.5 inches clear cover, then ASH may give reinforcement which may be twice than this one. Okay, so in case of shear wall, this formula does not need to be satisfied. Only this formula needs to be satisfied. Okay, so if you have an Excel or program already which is prepared for a special moment frame column, then you can modify that Excel by just removing this formula or making it 0. And then there is another small change, that is under B1, the spacing of transverse reinforcement. Okay, vertical spacing of the transverse reinforcement. The code says for column that it shall be lower than 1/4 of the minimum dimension. So in case of shear wall, the minimum dimension is the width of the wall. Okay, if we look at this again, then this B is the dimension, lowest dimension of the shear wall. So B/4 was the formula in case of column. B/4, 1/4 of the minimum dimension. But in case of shear wall, you can take it B/3. Okay, so if your wall thickness is 12 inches, then 12 divided by 3 will be 4. But in case of column, it was supposed to be 12 divided by 4 equals 3 inches. So there's a great relief here. So it's a good thing. Now, let's go to the model and check it out. What is the minimum boundary element requirement from the model? So let's design it. While you check out the boundary element length, of course, apply the final pier section. If it is uniform reinforcing, then provide the correct uniform reinforcing. If it is general pier reinforcing, then apply the correct general pier reinforcing. So it is very important because the flexural reinforcement you provide plays a role in calculating your boundary element diameter. This is because in the calculation of the boundary element length, we have seen that C is involved. C is the length of the compression from the compression phase to the distance of the neutral axis. So, and again, C is calculated using this formula, which is derived from the book of the McGregor. So, using the simple beam displacement diagram, something like that, the length of the neutral axis can be calculated using this formula, alpha plus omega divided by this, where alpha equals this and omega equals this. Omega involves the rho L. Rho L is the longitudinal reinforcement ratio. So it means that longitudinal reinforcement ratio is included in omega. So omega plays a role in calculating C. Therefore, you need to input the correct reinforcement while you calculate your boundary element length. Again, boundary element length is only required when C is greater than this. Okay, you can calculate this based on the data you have, HW, delta U, and LW, where LW is the wall length, HW is the wall height from bottom to the top of the wall. And it is written here, HW refers to the total wall height from critical section to top of the wall. So in practical case and in our case, and in most of the cases, this is the wall height. From critical section means the wall bottom and top of the wall. to the top of the wall. This is a HW. LW is known. If it is a single wall like this single segment, then you know the LW. But if it is a compound wall, then it may be a little difficult to find out the LW. So there are other ways to do it. Rather than calculating the C value, you have an option to check out the stress in your wall. If the wall stress is greater than 20% of F prime C, then special boundary element is required. And if the wall stress is in between 20% and 15% of F prime C, then you need to provide ordinary boundary element. And wall stress, if wall stress is less than 15% of the F prime C, then you may do away with any boundary element. You do not need to provide any boundary element in this zone. But in our practice, we always provide a special boundary element from bottom to the top of the wall. And of course, remember to continue your hoops reinforcement into your foundation if the distance from the wall edge to the foundation edge is very less. There is a code requirement regarding that. It's probably if this distance is less than this height divided by 2, then you have to continue this. But if there is enough space like this, then you can only you have to only extend the boundary element hoops reinforcement into the foundation for only 300 mm depth. Okay. And since all the things are covered, now let us move to the ETABS model and see how much boundary element length is required by the code. So general pair reinforcing is what we were supposed to apply. It's now uniform reinforcing. Let's apply the general pair reinforcing, which we had finalized for our model. And then open the shell design output calculation summary, and then go to the last page. In the last page, you will have the boundary element length, edge length. Okay. So as we had previously pointed out, that leg 1 is this one, leg 2 is this, leg 3, and this one is the leg 4. So leg 1, the model says that it doesn't require any boundary element. However, there is something I didn't activate probably in my load combinations. Always check the load combinations. I probably did not incorporate the response spectrum load combinations. So let's incorporate them. And then check the design again. Where are we now? Now we are in the boundary element. Check. Yes, here. So boundary element, after you consider the response spectrum case governs here because response spectrum has been scaled to 100% of the static base here in our case. So my practice is that for designing the vertical elements, I always consider 100% of the scaling is 100% of static base share. If the response spectrum base share is less than that. In our code, which is BNBC 2020, it actually allows 85% scaling. However, for vertical element design, I choose to use 100% scaling. And for beam design, I choose the 85% scaling because I want to keep my beam design ductile, and hence I want to provide their less reinforcement so that beam column capacity ratio and etc. These issues do not arise, and my column doesn't become weaker due to providing higher reinforcement in the beams. So this is our approach. So in response spectrum, when we incorporate or include the response spectrum load combinations in the load combinations, then this governs, and then we have the edge lengths, boundary element lengths here. So leg 1, as I have already said, this one is a leg 1. It requires only 18 inches. So from this edge, you need to go up to here, 18 inches, and from here, probably from this space, probably I would go here something 18 inches, or from center actually I would go 18 inches. And then for leg 2, it is 12 inches. So from center I will go to 12 inches. So why center? Because ETABS already considers this wall from center to center. So that's why I'm considering the center. Someone may say from the edge, I wouldn't argue with him. I would also accept that. Leg 2 is done. Leg 3 is this one. Here you need to provide 20 inches from this edge to here, 20 inches boundary element, etc. So what is the maximum? At the bottom, it is actually maximum. Top doesn't matter. We should have checked the bottom boundary element requirements. So it is 28 inches. So it is the highest one. For leg 4, this is a leg 4. Leg 4 requires very less amount of edge length. But we will consider this as a boundary element. This complete portion will be considered a boundary element from this point to about, this is the leg one, about 21 inches or 26 inches we have to move from the center. So from say like this, we will consider this a boundary element. This and this. So this will be totally a boundary element. Here we will provide a boundary element. Here we will provide another one. Here the overlapping will occur. Here we will do like this. Here we will do like this. So this will be our boundary element. Here we do not need ties, but providing ties is better, because providing ties lets you consider your distribution reinforcement as reflects the reinforcement cardboard. So for the distribution reinforcement, you can provide ties at a spacing of 14 inches or 12 inches on center. Let me show you now a drawing where boundary element details have been drawn. This is actually not our wall, because we didn't yet prepare the drawing for our structural shear wall. I'm showing you another case from here. So if it is a straight shear wall, then you will have some boundary element at the ends. Here, about 19 inches was the requirement, or 18 inches. Actually, it wasn't my design, though my supervision was involved in it. Rather, I would prefer 24 inches minimum if it is 19 inches or something like that. What you have to do is you have to provide your dense reinforcement here in this boundary element, and you can provide a row of reinforcement here as well. And for this reinforcement, you may use lower dia reinforcement. As an example here, 20 mm dia reinforcement has been used, and here 12 mm dia reinforcement has been used. And you can specify a higher spacing here, 8 inches, 12 inches, etc. However, check out the minimum requirement, which is probably 0.0025, 0.25% of the gross section. So you can always check it from your code, BMDC 2020 or some other code. For example, in our case, the distributed reinforcement has a minimum requirement of 0.25%. However, it can be obviated or reduced if these conditions are met, etc. However, I would suggest to use a 0.25 minimum reinforcement percentage. So so here you provide all your hoops reinforcement as per the code requirements, which I had shown you here. This criteria has to be fulfilled. And then here you can provide tie spacing at a spacing of say 12 inches or something like that, or since it is 6 inches, then you are providing at every 12 inches. So it's okay. But I would suggest not to exceed 14 inches. However, you can do away or even not use any tie here, but I would suggest to you using ties here, transverse reinforcement here, so that you can use this reinforcement in your special shell or seismic shell as well. And use 14 inches maxillary spacing, but try to use lower than that. Now, in our case, for example, it is 12 inches tie spacing here. And your shear reinforcement, which is this, I don't know what they have drawn here. It should be like this. Okay. Like this. Your shear reinforcement, which we had decided to provide 16 mm diameter rebar at the rate of 4 inches center to center vertically. This should be bent into the boundary element, and the rebar development length has to be ensured. Say if it is 19 inches, so it means that 16 mm bar dia requires about 30 inches of straight development length. So it indicates that straight development length is not sufficient, so you have to provide a standard hook at the end. And the code requires that you provide this end or bar end should be in 6 inches from the edge of the wall. Okay. So in 6 inches, it must be located. It is automatically satisfied in our case. And of course, your hoops must satisfy the hoops detailing requirements. For example, this should be 6 dB, etc. There are other requirements which I'm not going through now. And in case of a compound shear wall, the only complexity you have is at the junction. Okay, at the junction. So at the junction, how you will arrange your hoops, this is a matter of concern. So you can arrange your hoops like this. This is a complete hoops. complete hoop. This is a complete hoop, and they overlap on each other. And this should be good because this hoop interlocks this hoop. So this is a good practice. So the corner should be well protected. I think the boundary element design should be clear to you, and it should not be any problem in detailing such boundary elements in future. I hope. Okay, good luck. Thank you being with us. Thank you for being with us.